Okay, chapter 7, lecture, uh, the very important concept of momentum and conservation of momentum, together with conservation of energy, uh, allows you to solve pretty much everything in terms of collisions. We invented the concept of momentum to solve collision problems. No matter what the collision is, elastic, inelastic, momentum will be conserved. So overall momentum for the system is conserved is a very powerful statement to solve all sorts of collision problems. And then the inverse of collision would be the explosion. And guess what? Conservation of momentum also applies for all sorts of explosions. And every time you see those fireworks, you see how they are kind of symmetrical. And the symmetry comes from the conservation of momentum principle. So every time you see some kind of a collision and then a bounce or they stick together, it's a sure sign for you to use conservation of momentum. And the concept of center of mass, that's what we're later going to use for rotation. That's an also important concept. So with no external forces around, energy is conserved. And what is also conserved is the linear momentum. We have angular momentum that we'll discuss for rotation as well. For now, it's just linear momentum. Now, what is momentum? Momentum is a vector. And you know right away that if it's a vector, it has two things, magnitude and direction. And for calculating the direction, it's very easy. It's the same as the direction for velocity of an object times the mass of the object. That's the product between a scalar and the vector. It's a vector, and the momentum has the same direction as the velocity vector. So mass times velocity. Mass is in kilograms. Velocity is in meters per second. So unit-wise, it is kilograms times meters over seconds. Once again, you can see how base units represent something that is not just regular units. And you can only change momentum if there is a net external force. This is the statement for the second Newton's law that Newton actually figured out. Because for change in momentum, you can change the mass, or you can change the velocity, or you can change both. So no matter what the change is, mass or velocity or both, you have a change in momentum, and you can only change it if you have a net external force. So our statement for the second Newton's law was F equals ma, because mass was considered constant. Now we have to get away from it because Newton never said so. Newton said change in momentum. Definition for acceleration is from kinematics, change in velocity with respect to time. Here we go. Substitute for acceleration. That's what you're going to get. So net external force is mass is still there, and acceleration is change in velocity over time. Now you can see that mass times the change in velocity is actually the change in momentum. And for change in momentum, you can say it can be a change in mass or velocity or both. So the most general scenario, change in both, represents the change in momentum. So your m times v is replaced with the change in momentum. So the rate of change of momentum is equal to the net external force acting on the particle. And what's the direction? of that net external force, it's the same as the change in momentum. Once again, be careful. It's not the momentum itself. It's not the initial momentum. It's not the final momentum. It's the delta. Delta is the change. Final takeaway initial. So for change in momentum, it can be a change in mass or velocity or both. So this is the most general statement for the second Newton's law. And that's exactly what Newton said. Newton never said F equals ma. Newton was genius enough to say, hey, how about changing mass? And let's say you're solving a problem for a rocket. You know how rocket is 90% fuel. And once the rocket is out in the orbit, it has lost 90% of its mass because it has burned all that fuel. So definitely a change in mass for that object. And you can't just say F equals ma for that rocket accelerating into cosmos. So change in momentum takes care of both changes, mass and velocity. So here's the graph of momentum versus time. And you have to rank the regions 1 through 4 according to the magnitude of the force that changes the momentum greatest first. Well, let's go back to the formula. What is the force? You can see how it's change over change, rise over run. So the force will represent the slope. Every time you have rise over run, it's the slope, definition of a slope. So if momentum is the function, t is the variable, then change in function over change in variable, force is the slope. So what do you say for the slope? For region 1, it's the steepest slope. It's much steeper than 3. And clearly you have the greatest value for the force because the slope produces the most change in moment. For region 2, what do you say? Momentum stays constant. There's no change in momentum. Therefore, change is 0. So the force must be 0. For region 4, same thing. Momentum is constant, no change. Change is 0, so force is 0. And region 3, what do you see? The slope is negative, so the force is negative. So that's why 1 is the greatest. 2 and 4 have 0 slopes, 0 forces, 0 net external forces. And region 3 is the lowest amount because it's the negative slope. So as I said before, no matter what the collision is always a conservation of momentum. And we will discuss that. The reasoning is the third Newton's law. You say that momentum before the collision for the system as a whole equals to the momentum of the system after the collision. And let's think about two balls that, like two pool balls. If you ever played pool, you've seen those balls collide and bounce. So think about two balls going head to head. So there is a collision and then the bounce. What do we have here? Well, there is a certain momentum for ball A. There is a certain momentum for ball B. And for ball B, it's going to be a negative value because if rightward direction is positive, then momentum to the left would be with a negative sign. And during the collision, what do we have? We have two forces. First force is ball A hits ball B, so force AB. And then because for every action there is equal and opposite reaction, there is an equal and opposite force from ball B onto ball A. So you got FAB and FBA, and you should put a negative sign in front of one of those vectors because forces are opposite, and you set them equal to each other in terms of magnitude. So action-reaction pair of forces, and they're exactly the same magnitude, opposite direction. What kind of a change in momentum do we have? Well, for force AB, there is clearly a change in momentum for ball A because it hits ball B, and ball A bounces back. But what do we have for ball B? We have the same picture. There is a collision with ball A, so ball B has to bounce back. There is clearly a change in momentum for ball B. And what kind of a change is that? Well, if forces are the same, then change in momentum must also be the same. And one change would be in the positive direction, the other change would be the same magnitude in the opposite direction. You add up both changes, what are you going to get? You're going to get an overall zero change. So forces are the same. So left side of the equation is the same. Time is the same for both. So change in momentum must be the same. And because momentum is a vector, one change is, say, in positive direction, and the other change would be in the opposite, negative direction. And you add up stuff as vectors, you end up with zero change for the system. Once again, there is a change for the first ball. There is a change for the second ball. But then you combine both changes, and you get the overall zero change for the system of two balls. That's why, no matter what you do, no matter the collision, you will always get zero change in momentum. And the statement for the second Newton's law is the net external force acting on the system of two balls is zero. Yes, you do have a force AB. Yes, you do have the force BA. But then you add them up and you get zero net force. So if you don't have any mass that leaves or enters the system, if you don't have any external forces acting on the system, then total linear momentum cannot change. And this statement is what we're going to use for all the collision and explosion problems. Now, I recommend you never say momentum as a vector is constant, because see how for this condition you have to have no external forces. And you have to remember that there is always gravity. And even if you go to space, there is still gravity. And gravity would be that net external force that will act on objects and will ruin this statement. At least for the x-axis, that's definitely not a good force to have. And for y-axis too. So for problem solving, I suggest you never say the momentum as a vector, but let's say just the x components. P sub x is equal to P sub x after the collision. And for that momentum, you can solve for what's missing. So here's a little example. We got two railroad carts. Cart B is at rest. Cart A moves towards cart B at a certain speed. And the way you say what's going on before and after collision, you say P sub x before is P sub x after. Because there is a collision, momentum is conserved. And in order to solve for the final speed when they couple together and move in that direction, you state that the momentum in the x direction must be conserved. Do not say P as a vector, because for P as a vector, you have to consider y-axis, z-axis, all other axes, and there is gravity acting. So do not ruin your statement for conservation of momentum here. So what you would say would be mass of card A times 24 plus mass card B times 0 would be equal to mass A plus mass B times the V prime, which is the unknown statement, the unknown quantity, and you can solve for V prime right away. Let's take a look at this question. We have a ball bouncing from a vertical wall with no change in speed. Be careful, see how there is a change in velocity, but it says no change in speed. That means magnitude is the same. So what is the change in momentum onto x-axis? So here's the x-axis, and this is the momentum before, and this is the momentum after, because it's going to be the same direction as velocity. And the change is the key word here. It's not the before, it's not the after. The question is, what is the change in momentum onto x-axis? Let's see what kind of a change we're talking about. Well, if this is the momentum, then this is the component, x component of the momentum before. This is initial, this is final, final minus initial. You have a rightward component for the momentum right here. And after the collision, that's the direction for momentum. You can see that onto x, you have the same amount, same component. And that's why the change is 0. You don't have any changes onto x-axis. You change the direction in terms of vertical component, but x-wise, for x-axis, you don't have any changes. That was the component before. That's the component after. Same direction. They're both positive and same magnitude. To be more specific, if this is theta, then this is theta. So it would be sine. So mv sine theta and mv sine theta here as well. So initial would be the same as final and no change overall. Now, same setup, and we have to discuss change in momentum onto y-axis. For y-axis, before, that's the component, and see how it's a negative component. And after the collision, that's the component, and now it's a positive component because it's final takeaway initial. Final is going to be a positive value, initial is 0. So you have positive momentum onto y-axis after the collision and negative before the collision. So change is final takeaway initial. Final is a positive value. Take away a negative value. If you're taking away a negative value, minus and a minus makes it a plus. So it's something positive plus some more positive. The overall change must be positive. And what kind of a change? How much of a change? It's going to be exactly mv with cosine theta here and cosine theta there. So it's going to be double the mv cosine theta. And direction is along the positive y-axis. This is the final. Take away initial. Take away, remember how you subtract vectors? You add the opposite. So this is the final. The opposite of the initial would be what? North of west. So this plus north of west, you will get the vertical direction for the change in momentum, which makes it normal force is the suspect for this kind of a change, and that's exactly the force that will change our momentum. You got the change is vertical. Remember, normal force is perpendicular to the surface. The surface is horizontal, and perpendicular to that horizontal, you got the normal reaction force from the wall onto the ball. So normal force generates the change in momentum. Normal force is your net external force. And that's why you change your direction, and change in direction is a change in momentum. Now, for the change in momentum, you can also define impulse. Instead of saying change in momentum, for some reason, textbooks like to say impulse. Well, it is what it is. So if you don't like to say change in momentum, you have to say the word impulse. Let's go back to the second Newton's law. How would you solve for impulse? Well, multiply both sides by delta t. Delta t cancels on the right side, and on the left side, you'll get the net force times the delta t. That's exactly the definition for impulse. The impulse, which is the change in momentum, like literally, is the product between the net external force and the moment of time that this force acts on the object. Yeah, you can think about a ball that hits the racket, the tennis racket. And what's the impulse for the ball? Well, that would be the force from the racket acting on the ball times the time that the collision took place. So, say 3 milliseconds or 5 microseconds, whatever the time is, times the force from the racket on the ball. That would be the change in momentum for the ball. And once again, if you don't like delta P, the change in momentum, you can say capital J. Capital J is what we define as impulse. Technically, you really don't need the impulse. You can just say change in momentum. That's perfectly fine, in my opinion. But the book has it, so here we go with the impulse definition. For this class, we're not going to do any calculations of the area below the force versus time curve. What we will do most of the time, we'll just be dealing with average forces. And average would be, minimum plus the maximum divided by 2. So to keep things simple, like whatever is the maximum force that is given for your average force for calculating the change in momentum, you can just go with the average. That's perfectly fine for an algebra and trigonometry based. For a calculus class, of course, you will do the antiderivative and calculate the exact area below. That would be the way to do it, but not for this class. Don't worry about the exact area, timing, just use the average force. Okay, question for you. We have a paratrooper and his parachute never opens. He lands in snow. He's hurt but alive. If he would have landed on the bare ground, then time would have been 10 times shorter. Any collision, of course, would be lethal. So what's going on with the snow in terms of change in momentum? Well, for change in momentum, it's the force times the time. We say that the time is 10 times shorter for the ground, and force would be stronger. So less time, much more force, and that's why the paratrooper would have been dead. Compared to landing in snow, it's 10 times longer time, and the force is less. That's why the paratrooper survives. But the change in momentum is also what? Mass times velocity. Mass stays the same, and change in velocity is also the same. That paratrooper had a certain velocity right before he or she has hit the ground versus, and then the final would be the zero because eventually he or she stops. So the change is zero, take away a certain value, and that value is the same. So the change is the same. Change in momentum is the same, it's unchanged. And you might say, hey, forces are different, timing is different. How is that possible? Well, it is possible because change in momentum is the product. More force, less timing, or more timing, less force, you will get the same product. Say 2 times 5 versus 5 times 2. The product is 10 anyways. So the change in momentum is the same, even though the forces are different and timing is different as well. Same story. And now, how about the value of the impulse? You say, very easy. Impulse is what? Impulse is defined as change in momentum. And we just figured out that change in momentum is the same for both cases. So if the change in momentum is the same, then impulse is the same. So no change for impulse as well. It's the same change for both cases. And finally, does the snow increase or decrease the values of the force? And now for the force, you say what? If the time is 10 times shorter, then the force is 10 times more. And that's what kills the paratrooper. So force is stronger for the ground and much less for the snow. That's why the paratrooper survives. So you really want to be careful on answering those questions. Read the question. Is it about the force? Is it about the timing? Or is it about, okay, let me mute that person. Is it the force? Is it the timing? Or is it the change in momentum, which we call impulse? Look at the formula once again. Timing can be different. Force can be different. And change in momentum can be the same for both scenarios. It really depends on those two parameters. Remember how we said for the third Newton's law that forces are the same, but force is mass times acceleration. And when, say, a mosquito hits a truck, the force on the mosquito from the truck is the same as the force on the truck from the mosquito, but mosquito has much less mass and much more acceleration, and that's why mosquito dies. For the truck, much more mass, much less acceleration, and the truck says whatever, there's no acceleration, there's not much of a change for velocity for the truck. So same principle. Forces might be different, timing might be different, but change in momentum is the same. Now, you have two types of collisions. The first type is elastic, and the second type is inelastic. And what's good about momentum, it is conserved for all collisions. No matter what the collisions is, what type of a collision we have, momentum is conserved, and that's very good. That's very handy for problem solving. But if it's also given that collision is elastic, it means that there is no loss in kinetic energy. And you got to understand there's always going to be some loss of kinetic energy because they get together. There's a little bit of a contact and friction, and some of that kinetic energy will be lost no matter what. And then there is sound that you normally hear. Some energy will be lost for the sound as well. But if the losses are negligible, you can think of collision being close to perfectly elastic, and that means kinetic energy is also conserved. So not only you say P sub x equals P sub x before and after, you can also say the total kinetic energy before is the same as the total kinetic energy for the system after the collision or an explosion. So very helpful kind of a collision. If it's elastic, think about two billiard balls, two pool balls. That would be your approximation for elastic collision. You can think about the conservation of kinetic energy as well with that. So, of course, collisions are inelastic, all of them. Some waste of energy, of kinetic energy is expected. But if you can approximate them to be elastic, then you say kinetic energy stays constant for the system, and that helps to solve a lot of problems. So elastic collisions, the definition for elastic collision is no change in kinetic energy for the system. If there is a change for the kinetic energy, then it's an inelastic collision. So two balls get together, collide, and you say ball A with a certain mass traveling in a certain direction with velocity v sub A, and plus mass B, velocity B, both of them traveling in the positive direction. It's not always the case, but this time it is the case. Then the ball A hits the ball B, and they're still going in the positive direction, which is usually also not the case. You will have bounce back and negative direction for momentum. You have MAV prime A plus MBV prime B for the conservation of momentum. Now for elastic collision, we say kinetic energy is also conserved, and the kinetic energy of ball A before the collision plus kinetic energy of ball B before the collision is the same as kinetic energy of ball A after the collision plus kinetic energy of the ball B after the collision. So two equations, four unknowns in general. So if you know the other two parameters, you can easily solve for the remaining two parameters. And you don't have to do anything else, just go with conservation of momentum and kinetic energy. If the collision is elastic. If it's not elastic, of course, you can't say the second statement, but the first statement is still there. So first statement, conservation of momentum, will apply to both elastic and inelastic collisions as well. Second statement is optional, and it's only there when it is elastic. Be careful. So inelastic collisions means that some of the kinetic energy is lost, and it was converted into thermal energy, or maybe potential energy, maybe the sound. So all of that is an option. The point is, you cannot say 1/2 mv squared plus 1/2 mv squared equals 1/2 mv squared plus 1/2 mv. You can't say this anymore. And one of the options for inelastic collision would be the perfectly inelastic, we say completely inelastic collision. That means that objects stick together and they move as one system. So it was two systems, say ball A and ball B. Now they stick together and it's the same. And for the total mass, you say mass A plus MB. So two masses added up together, they move as a whole. So let's take a look at the conservation of momentum for such a case. You have the first ball, you have the second ball. The second ball is sitting still before the collision. The first ball is going towards it with a certain velocity. Now, after the completely inelastic collision, two balls stick together. So it was P sub x before, which was m1 v1 initial in the positive direction, and the second momentum was just zero because it was sitting still. And after the collision, you got m1 plus m2, and they move with the same velocity in that same x direction. So this is your P sub x before and P sub x after statements that you set equal to each other, because for every collision, momentum is conserved. So completely elastic, completely inelastic, momentum is still conserved. And this is your ballistic pendulum lab that we'll do later. What you have here is a bullet that hits a box of sand, and then the bullet sticks in that box, and because of the collision and some momentum transferred to that box of sand, you have motion of the bullet and the box to a certain altitude. So this little problem combines it all. Because there is a collision, you have a conservation of momentum statement. And also, once you figure out the initial velocity of the system right after the collision, and you realize that once it reaches the topmost point, it stops, you can solve for the initial velocity of the bullet from the conservation of energy. Because there's no air resistance, you can solve the conservation of energy. So P sub x before equals P sub x after. P sub x before, it's just the little mass of a bullet times the speed of the bullet, positive direction, plus 0. 0 stands for the box with the sand, which was just sitting still before the collision. And after the collision, both masses are combined because the bullet embeds itself into the box. So masses are combined, and they both travel at the same speed v prime. Positive direction, so everything is positive. So from the first equation, you can find the speed for the system right after the collision. And this little speed becomes the definition for the total kinetic energy of the system, 1/2 mv squared. Remember the equation? Well, it's not just m, it's both masses combined, and the initial velocity right after the collision that we use for the total energy of the system right after the collision. And then the system is flying up into the air and reaches a certain altitude, the height, h. And remember the gravitational potential energy that you transfer your kinetic energy into mgh. It's not just m, it's both masses combined, and gh is still there. So from here, you can solve for how high the whole system goes to, the maximum altitude, or if that altitude is given, you can go back and solve for the initial velocity of a bullet. This is exactly the way how detectives use, like they test different guns. If you want to know what kind of a gun was used at the scene of death, somebody was killed, and you want to know what kind of a gun was used, you look at the bullet, and you can figure out what kind of a bullet was it and what was the muzzle velocity for the gun. You can easily tell what kind of gun was used for that kind of a shot. So every time there is a new gun on the market, the very first thing police does is they test the bullet's speed. The muzzle velocity means the initial velocity out of the barrel of a gun, and they would fire those bullets in a sandbox and see how much of a change in altitude will that box gain, and they will measure the muzzle velocity. So conservation of momentum because there is a collision, and conservation of energy. Kinetic energy equals to potential because there is no friction. Those are the two physics concepts to solve for the either initial velocity of a bullet or how high the box with the bullet goes up. Very handy concepts. Now collisions in two dimensions. It was collision in only one dimension, just x. Now, let's say we have not a head-on collision, but collision to a side. Say, if you hit a pool ball from the side, it will not go straight. It will go at a certain angle. And in order to determine that angle, you have to draw a diagram, show the reference angles, and good news, you still apply conservation of momentum for each axis because the total momentum stays constant. There might be a change in x direction, there might be a change in y component, but the overall change has to be 0 compared to the conditions before the collision. So this is what I'm talking about. Two balls get in contact. M1, M2, so masses are given. The second ball was sitting still, and the first ball hits it at a certain angle. And it's theta 1, that's the reference angle for the first ball. And theta 2 is the reference angle for the second ball. So clearly a two-dimensional collision. You have some change in x components, you have some change in y components. You have to treat them separately, like we did the projectile motion problems, remember? Horizontal motion, vertical motion, and then you combine them together. So this time it is the same setup. Along the x-axis, what do we get? We have the initial momentum for the first ball, and it's just a positive value, same direction as x. For the second ball is 0 because the ball is just sitting still. So m2 times v2, and v2 is 0. Now after the collision, the first ball goes this way, and your x component is the side that is adjacent. And if it's adjacent, then it's the cosine function. So this is your momentum after the collision for the first ball. And the second ball goes in this direction. You can also see that x component is adjacent to theta 2. So if it's adjacent, it's the cosine function. And the second ball gains this much of a momentum. And the overall momentum must be the same. Whatever you had before will be split into between the two balls. And x component is conserved. Now, what do we have for the y components? For the y component, the first ball is perpendicular. The momentum from the first ball is perpendicular onto y-axis. So if it's perpendicular, the component is 0. Second ball is sitting still, so that component is also 0. So it's 0 plus 0. Before the collision, that's just 0. After the collision, one ball goes upward and the other ball goes downward. And if it's a downward, then the component is going to be negative. So it's a negative m1v1 final. And if this is theta, then this is theta. And we're talking about y component, which is opposite to theta. Therefore, it's the sine function. And it's negative once again, because v sub 1 goes in the negative direction for y-axis. Now the second ball goes upward, which makes it a positive component. So it's a plus m2v2. That's the momentum. And If this is theta, then this is theta. We're still looking at the side that is opposite to theta. So the function is the sine. So here we are, two equations for two components, x and y components. Overall momentum is conserved for both components because no matter what the collision, momentum for the system is conserved. Energy-wise, well, if it says elastic collision, then for those balls, you say 1/2 mv squared from the first ball plus a 0 is 1/2 mv1 squared, which was the second, which was the first ball going downward. That's the kinetic energy, plus the kinetic energy of the second ball moving in the other direction. So energy-wise, you can only do this if it's given as elastic. If there's an elastic collision, then kinetic energy for the system is conserved as well. So maximum, you have 1, 2, 3 equations and 7 unknowns. So in order to be able to solve the problem, you need to know 4 things, and then you can solve a system of 3 by 3 and solve for the remaining unknown parameters. So I want to point out that it's exactly the same procedure that we did for projectile motion. You analyzed horizontal motion, you analyzed vertical motion, then you combine the equations because time goes the same way for x and y components. Same thing here, time goes the same way for x and y components, and overall momentum is conserved for both components. If it's elastic, then life is beautiful. You just have to conserve kinetic energy, and that's it. If it's inelastic, then you just can't say this statement, and you try to solve from what's given otherwise. So something that we did before. For the center of mass, once again, the majority of the problems dealing with calculations of center of mass is for calculus-based class. For this level, it's just a brief introduction and the importance of finding the center of mass, and you will calculate those things later in the calculus-based class. The hard part is left for the calculus class. So what is so special about the center of mass? Well, think about a baseball bat that you flip into the air, and you will see that the bat will move as a projectile, and it will also rotate during the projectile motion. So what we call the center of mass corresponds to a special point for which motion is translational. So the center of mass is this black dot that you see going, which never shows any rotational motion. This dot, this particle, this specific point on the object is the point that undergoes the translational motion only. No rotation for the center of mass. So once you figure out the center of mass, you can solve a lot of things just from the projectile motion perspective, and then you add rotation, which we will discuss later after test 2, and solve the second part of the problem. So finding the center of mass allows you to squeeze the bat to a point and just think about the bat as a point doing the projectile motion, which is quite a simplification and allows you to solve those problems rather easy. So center of mass, this time it's going to be a parabola, projectile motion, duh. Just as a regular tossed ball does. All other points rotate around the center of mass, and we only are interested in the center of mass because it simplifies any given motion, and there's no rotation to consider whatsoever. You can just do projectile motion calculation. So here's the formula to find this special point. Let's say you have 2-point masses, M1 and M2, and you want to find the center of mass. In order to find this point, you take the first mass multiplied by the x1 coordinate. Then you take the mass 2 and you multiply by the x sub 2 coordinate. And then you divide by the sum of masses. This is the easiest scenario. Once again, for calculus-based class, it's going to be the antiderivative approach, the calculus-based approach. None of that applies here. It's just the simplest possible scenario. Get the masses, get the positions, and that's it. This is going to be the x coordinate for the center of mass. If you have more than 2 masses, the formula doesn't change much. It's m1x1, m2x2, and then you just add the third mass at a certain x coordinate, and the fourth, and the fifth, and all the way up to whatever the amount of masses you have in your system, times the position of a certain mass, and you divide by the sum total of all the masses. So m1 plus m2 plus m3 plus m4 plus m5, this is your capital M. Capital M is the sum total of all the masses. So where is the center of mass of the plate originally? Well, I'm pretty sure you've seen those plates and you found the symmetry from your personal experience. You might say right away the origin. X is 0, Y is 0, right in the middle. The intersection of diagonals, or whatever method you choose, you will find the symmetry at the origin. Let's say you remove square 1. Let's say this whole piece is missing. Then, what is it? Removal of square 1. So the whole thing will move in the third quadrant along y equals negative x. Squares 1 and 2. So remove 1 and 2. It's going to be along the negative y-axis somewhere here. Squares 1 and 3. So only 2 and 4 are left. You go back to the origin. And 1, 2, 3. If it's only the fourth square that is present, then it's going to be right in the middle. Along y equals x. And quadrants x, all 4 squares, once again at the origin. So the moral here is it's just the introduction. This is the simplest formula. The real formula means antiderivatives. We're not going to go deeper into that. But as for just brief introduction, that's enough to think about this formula. For the explosion, exactly the same process. Consider explosion as the opposite of collision. So momentum is conserved. So all the pieces that go in one direction must be counterbalanced by all the pieces going in the opposite direction. That's why those fireworks have such cool symmetry. Ignoring air resistance, of course. So if there is an explosion, you should also consider conservation of momentum. Whatever you had before, probably say a grenade that is split into different pieces. Before the explosion, it was just 0. After the explosion, those pieces of grenade will fly in different directions, but the total momentum after the explosion is still 0. Same as before the explosion. Okay, so initially stationary device explodes into two pieces, one of them in the positive x direction. What is the sum of the momenta of the two pieces after the explosion? Okay, what did we have before the explosion? Well, it was just lying stationary. So what's the velocity? Zero. Mass times velocity, mass times zero gives you zero momentum for the system in the first place. Now, after the explosion, the sum total of all the momenta must still be zero. It is a conservation of momentum principle that is right here, and you have to remember that for any collision or explosion, whatever you had as momentum before must be the same as total momentum after the explosion or collision. If before it was a zero, then after it's also zero. Same setup, two pieces across the floor, one of them in the positive direction, I believe positive x direction, x is missing. Can the second piece move at an angle? Oh, okay, let's do the whiteboard so that I can show you what's going on. It's the last slide anyways, so for the whiteboard, you got the before the explosion, it was just one piece, and momentum is zero. After the explosion, one piece goes in the positive x direction at a certain velocity. So what's going on with the other piece? Well, the total momentum must still be zero. So the other piece should go exactly in the opposite direction. If that piece goes, say, in this direction or that direction, that will violate the conservation of momentum right away, because you didn't have any y components in the first place. Y components was zero. And now you have x component and y component. Y component or y component there, which cannot be balanced by any y components from the first piece. So there is no way that the second piece will go at an angle. It can only go exactly backwards. This way, momentum can be conserved. You have a positive x component, which will be balanced by the negative x component, and you will get overall zero momentum for the system. If the second piece goes at the angle, then, well, you have to do something for the first piece at an angle as well. Otherwise, you're violating the conservation of momentum. So the idea behind should be clear. Multiple sharing, yeah, let's try multiple sharing. No. Whiteboard, yes, I want to close it. I just want to go back to the, okay, I believe I lost that presentation thing. Anyways, that was the last slide for the presentation. I'm gonna stop recording.